If a free particle described by a plane wave and moving in the positive z direction undergoes scattering by potential, Vr is equals to V0 for r less than r and 0 for r less than r. If V0 is changed to V0 keeping r fixed, then differential scattering cross section in the Bohr approximations are. So these are the values. Whether it increased 4 times of original value, increased to twice the original value, decreased to half the original value, and decreased to 1/4 of the original value. Now, solution. We have V of r is equals to V0 0 if r is greater than r and if r is less than r. The differential scattering cross section in Bohr approximation is defined as del sigma by del omega is equals to f theta phi square, where f theta phi is the scattering amplitude and its value is calculated as follows. F of theta phi is equals to minus 2m by h square q 0 to infinity r sin q r v r dr. ठीक है. Now further, that means this is equivalent to a into v0, where a0 is defined as minus twice m h square q into r sin qr v of r dr. Function r constant we have taken outside. So for the current problem, v0 is outside, so we can simply write it down, this term. Now, so differential cross section becomes del sigma by del theta is equals to f mod f theta phi square equals to a square v0 square. If v0 is changed to v0, the differential scattering, we can say differential scattering or sigma 1 theta differential cross section becomes del sigma 2 by del omega I have wrongly written theta equals to a square into 2v0 square, that is 4 times of sigma 1 theta. So our differential cross section increases to 4 times of the original value. That means option A is correct answer for this problem. A variation calculation is done with normalized trial wave function given by this for a one-dimension potential 0 between minus a to a and infinity otherwise. So ground state energy is to be estimated to be solution. We have v of x is equals to 0 to infinity, mod x is less than a and mod x is greater than a. The Hamiltonian corresponding this potential is h is equals to minus h square by 2m d square by dx square plus vx equals to minus h square by 2m d square by dx square. The normalized trial wave function is psi of x is equals to root over by 16 a की power 5 a square minus x square. The ground state energy is 0 corresponding to the given Hamiltonian is 0 is equals to psi h psi equals to integration psi star minus h square by 2m del square psi by del x square dx, which reduced to minus h square by 2m psi star del square psi by del x square dx, or we can write it down minus h square by 2m minus a to a square and further into 15 by 16 a की power 5 minus x square equals to minus 2 dx. That will be turning out to be 15 by 16 a की power 5 h square by m 0 to into 2 0 to a square minus x square dx. This term is turning out equals to be e would be 2 times into 15 cross square by 16 a की power 5 into m 0 to a square minus x square dx, which will give us 2 into 15 by h cross square by 16 m a की power 5 into 2 by 3 a cube, which would give us 5 by 4 h cross square by m a square. Thus, our answer for this problem is option D. A particle in one dimension is in potential Vx is equals to minus infinity minus x less than 0 minus v naught 0 x l 0 x greater than l. There is at least one boundary state. The minimum depth of potential is solution. The potential of a particle on one dimension is given by Vx is equals to infinity x less than 0 minus v0 0 x less than l 0 for x greater than l. The pictorial diagram for this is this is region first, this is region second, and this height is v0 and this region is second. This Schrödinger equation for the particle in first region is h psi first equals to e psi first implies psi first by del x square plus 2m by h cross square e minus v0 psi first equals to 0, or del square psi first by del x square plus beta square psi first is equals to 0, where beta square is equals to twice m by h cross square e plus v0. The solution of the above equation is psi 1 x is equals to a sin beta x plus b cos beta x. Now applying boundary condition. Boundary condition that is psi first at x is equals to 0 must be equals to 0. That means a into psi first at x is equals to 0 is equals to sin 0 plus b cos 0 equals to 0 implies b is equals to 0. Thus, wave function in the region first is given by psi first x is equals to a sin beta x. This Schrödinger equation for the particle and region second is, that is h psi second equals to e psi second, implies del square psi second by del square plus 2m by h cross square e by psi second equals to 0, implies del square psi second by del x square minus alpha square psi second equals to 0, where phi square is equals to minus 2me by h cross square. The solution of above equation is given by phi second of x is equals to c e to the power alpha x plus d e to the power alpha x, considering the limiting case limit x tends to infinity, psi second x must be 0, limit x tends to infinity psi second x equals to limit x tends to infinity psi c e to the power minus alpha x plus d e to the power alpha x equals to 0, implies d is equals to 0. So wave function in region second is given by psi second of x is equals to c e minus alpha x. Now applying boundary condition at x is equals to L. We get psi second at x is equals to L psi first at x is equals to L multiplied equals to psi second at x is equals to L, and continuity equation del psi first by del x at x is equals to L must be equals to del psi second by del x at x is equals to L. So a sin beta L is equals to c e to the power minus beta L. Further, this term implies a beta cos beta L is equals to minus c alpha sin o e to the power minus alpha o alpha L. This term is alpha. Dividing, let this equation a by b. Dividing equation V by A, V at cos beta L minus C alpha e की power minus alpha L divided by A sin beta L equals to C here it is beta C e to the power minus alpha L implies cot beta L is equals to minus alpha by beta. And if you multiply L and write it like, take it beta L is equals to J and alpha L is equals to eta. So our equation reduces to J cot J minus eta. And further, if we square and add J square plus eta square is equals to L square into beta square plus alpha square, that is turned out to be 2mv0 L square by h cross square. And this is equals to r square. Now, if we plot, let us plot cot J eta versus J curve. We are having it pi by 2 pi. So, and eta, this is J, the cot curve would rise from this region. Minimum wavelength of the circle should be just to touch it here, that is pi by 2. So, if r is equals to pi by 2, minimum wavelength to get one boundary state. For getting one boundary state, that is r square is equals to pi square by 4 implies 2mv0 L square by h cut square implies v0 must be pi square h square by 8 ml square. So this is minimum potential. Here range would be r की range would be pi by 2 less than r less than pi. So यहाँ से होगा minimum value, we can take it this one. Or here I can write it down for you guys. Pi by 2 r less than pi. So if this circle is greater than this pi by 2, then we would obtain first boundary state. The minimum value of potential to obtain one boundary state v0 is equals to pi square h cross square by 8 ml square. Thus our answer would be option A. Which of the following is a self-adjoint operator in a spherical polar coordinate system? Solution. An operator A is said to be Hermitian if it satisfies the following condition. Psi m a psi n is equals to a psi m psi n for operator a is equals to I h cross sin theta del by del theta. We have psi m is equals to I h cross sin theta del psi n by del theta is equals to minus infinity to infinity psi m h cross by sin theta del by del theta psi n sin theta del theta. Sines will sign cancel, so we would be left with I h cross 0 to pi psi m star. Here this term would be psi m star into del psi n by del theta into del theta, which would give us I h cross psi m star into psi n 0 to pi minus I h cross del psi star m by del theta into psi n del theta. So the first term would vanish out. We would be left with minus I h cross 0 integration 0 to pi del psi m by del theta into psi n del theta, which we can writing down as 0 to pi I h cross sin theta del psi by del theta conjugate star psi n sin theta del theta. Now we can write it down this as I h cross sin theta del psi m by del theta into psi n, which can be written as a psi m psi n. This since or that is a psi m a psi n is equals to a psi m by psi n, hence operator is Hermitian. Thus our answer is here. Even if we take it negative sign, there would not be any problem in the entire mechanics. Here that would positive, here is all negative. So our option would be C. Further one can see it, P is of the form minus I h cross del by del x. So P phi must be having same form minus I h cross del by del phi. But when we do it the integration of theta, there is additional term of sin theta d theta. So this term has to be in the denominator. That is from there we got this operator so that this term get nullify. Okay. So while doing the thing, just like when you do the integration for radial part, you just added r square d phi dr. When you do the integration of phi, you just write it del phi. So that is, but there is no additional term with phi, Lz is written as nothing but minus IH cross del by del phi. This sign term is in the denominator is there because there is an angular part in the integration. Just to make it Hermitian, this term has to vanish out. The spin orbit interaction in an atom is given by H is equals to A L dot S, where L and S are denote the orbital and spin angular momentum respectively of the atom. The splitting between level 3 P3 by 2 and 2 P1 by 2 is solution. We have H is equals to A L dot S. The total angular momentum is defined as J is equals to S implies J square is equals to plus S square implies J square is equals to L square plus S square plus 2 L dot S implies L dot S is equals to 1 by 2 J square minus L square minus S square. Thus, Hamiltonian takes the form that is H is equals to A L dot S equals to A by 2 J square minus L square minus S square, where eigenvalues J square, L square and S square are J square is equals to J plus 1 into J into H cross square. L square is equals to L into L plus 1 H cross square. And S square is equals to S into S plus 1 H cross square. Thus, the energy corresponding to this Hamiltonian is EJ equals to A by 2 H cross square J into J plus 1 minus L into L plus 1 S into S plus 1. The energy level for 2p3 by 2 is equals to S is equals to 1, L is equals to 1, J is equals to 3 by 2 is EJ equals to 3 by 2 is equals to A by 2, 3 by 2 into 3 by 2 plus 1. Here H cross square minus 1 into 1 plus 1 minus here this term would be 1 by 2. 1 by 2 into 1 by 2 plus 1. This term gives us AH square by 2. The energy level for 2p1 by 2, s is equals to 1 by 2, j is equals to 1 by 2, and l equals to 1 is e, j equals to 1 by 2, a h square by 2, 1 by 2 into 1 by 2 plus 1 minus 1 into 1 plus 1 minus 2 into 1 by 2 plus 1, that is minus a h cross square. So the splitting between 2p3 by 2 and 2p1 by 2 is delta E is equals to Ej equals to 3 by 2 minus Ej equals to 1 by 2, that is ah square by 2 plus ah square equals to 3 by 2 ah square. So correct answer is option A. We are discussing the CSIR Physical Science June 2012 Quantum Mechanics problems. Here we are having a 3.5 marks MCQ problem. Let us read the statement of this problem. The component along an arbitrary n with direction cosines nx, ny and z of a spin half particle is measured. The result is, so whenever the spin is measured irrespective of the components, its result would always be plus minus h cross by 2. Let us check it. Solution. I am saying in general, if a measurement is carried out, it would give us plus minus h cross by t, and that you can verify it from Stern-Garlick experiment as well. So Stern-Garlick experiment only give directions or only give eigenvalues plus minus h cross by 2. Further, spin along we have Sn can be defined in h cross by 2 sigma dot n cap. This term can be written as h cross by 2 and next 0 1 1 0 plus ny 0 minus I 0 plus nz 1 0 0 minus 1. We can combine this term. H cross by 2 is equals to nz into nx plusiny, minus nx plus iny minus nz is equals to h cross by 2 cos theta sin theta e to the power minus I phi sin theta e to the power I phi minus cos theta. Once we substitute the value of components nx, ny, nz. Now nx, what I am substituting it? Sin theta cos theta. Yes. ठीक है, and sin theta cos phi, here sin theta, substituting here nx is nothing but sin theta cos phi, ny is nothing but sin theta sin phi, and z is cos theta. So substituting these values were Sn reduced to this. Now the eigenvalue of Sn would be determined minus lambda I would be h cross by 2 cos theta minus lambda into h cross by 2 sin theta e to the power minus I phi h cross by 2 sine theta e to the power I phi minus h cross by 2 cos theta plus lambda equals to 0. So our result will be minus h cross by 2 cos theta square minus lambda square plus minus h cross by 2 sine theta square to 0. So our result will be lambda square minus h cross by 2 cos theta square minus h cross by 2 sine theta square equals to 0 implies lambda square would be h cross by 2 square into cos square theta plus sine square theta equals to h cross by 2 square implies lambda is equals to plus minus h cross by 2. Thus the eigenvalue of this matrix is h cross by 2. So our answer is option D is correct for this problem. A particle of mass m is in a cubic box of size A. The potential inside the box between x lies between 0 and a, y lies between 0 and b, a and z line between 0 and a is 0 and infinite outside. If the particle is in the eigen state of energy is equals to 14 pi h cross by s, its energy, its wave function is. So we have to determine the wave function corresponding to this energy. Solution. We know the energy of a particle inside a cubical box is given by E and x and y and z is equals to nx square plus ny square plus n equals to pi square h square by 2 ma square. But according to question we have 14 pi square h square by 2 ma square implies nx square plus ny square plus nz square equals to 14 implies nx, ny and z can take value 1, 2, 3. So that means there are 6 states. These are 1, 2, 3, 1, 3, 2, 3, 1, 2, 3, 2, 1, 3, 3, 2, 1 and 2, 3, 1. The corresponding the wave function corresponding to given energy eigenvalue can take any one of the above degenerate state. So psi is equals to 2 by a 3 by 2 sine pi x by a sine 2 pi y by a sine 3 pi z by a. Thus our answer would be option D. Let psi n LML denotes the eigenfunction of Hamiltonian for a spherical symmetric potential. The wave function 1 by 4 psi 210 root 5 2 1 minus 1 and 1 0 root 10 psi 211 is an eigenfunction only of solution. We have psi is equals to 1 by 4 psi 210 plus root 5 psi 21 minus 1 plus root 10 psi 211. Further psi is equals to 1. Now here we are writing some rule for eigenfunction. First, if value of n is same in each of the eigenstates of a function, then it is an eigenfunction. It is an eigenfunction of energy. Rule 2. If the value of L is same in all the eigenstates, then it is an eigenfunction of angular momentum. L. Third, if the value of ML is same in all the eigenstates, of the wave function, then it is an eigenfunction of Z component. Angular momentum. That is LZ. Now if we check it out, our wave function n is in this state is 2, in this state is 2, in this state is 2. That means it is an eigenfunction of energy oblique Hamiltonian. So it is an eigenfunction of H because n is equals to 2. Now L is 1, 1, 1. So if it is an eigenfunction of L as L is equals to 1, whereas ML takes different values, so it is not an eigenfunction of LZ. So our question would be H and L square. Option C, given wave function is an eigenfunction of L square and H. The commutator x square p square is this. We have to determine the value of commutator solution. X square p square can be written as x into x p square plus x p square into x. Further, this term can be written as x p plus px x p plus P into X P X. This term here would be XP plus XP into PX. So this value will be 2IH cross XP plus PX. Thus our option B is correct for this problem.